Good afternoon, everyone. I am Johan Jezekel. Thanks to be here today at Eurosatory for this roundtable dedicated to laser communication. And we will see how laser communication can be useful or helpful for military operation, especially in high-intensity combat. So I have the honor today to moderate this roundtable with this great panelist. We have an institutional representative from the CNES, Centre National des Études Spatiales, French Space Agency, Frédéric Lacoste. Please, Frédéric.
Thank you, Mr. Chairman. Good afternoon, everybody. I work as a project manager in CNES, the French Space Agency in Toulouse. And in particular with my technical team, I have the responsibility to implement two projects, the DISCRO project and the France Relance Co-op project led by AIRBUS Defense and Space, which are currently the two main frameworks to design and develop technologies for further free space optics for space applications.
Thank you, Frédéric. On his right, we have the chance to have Captain Jean-Philippe Vautier, Capitaine de Vaisseau in French, from the French Army General Staff. Please, sir.
Yes, good afternoon. Captain Jean-Philippe Vautier, I'm from the French Navy. During my career, I have been appointed on board different kind of ship, from the mine hunter to the carrier vessel, and I've been commanding a mine hunter and a surveillance frigate. Now I'm the officer in charge of the capability planning of the telecom domain at the French Joint Staff that is covering all the needs of the French Army, French Forces needs.
Thank you, sir. And we have Guimaël Denoroy from AIRBUS Defense and Space to represent the industry side. Please, Guimaël.
Sure. Yeah. Sure. Thank you. So good afternoon. My name is Guimaël Denoroy. I'm responsible for the LaserCom roadmap within AIRBUS. My job is to coordinate all the transnational development within a group, especially in Germany, the Netherlands, Italy, UK, and of course in France.
Thank you, Guimaël. Just to be crystal clear today, we won't talk about laser weapon, neither Star Wars. We will essentially talk about laser communication. And maybe before diving deeper into the topic, first, sir, could you explain us why communication are key in doing a military operation?
Thank you for the question. So the communications is the only means to transit orders and reports. It's the main usage in the armed forces. So the main characteristics that have to have the telecommunications is they have to be robust and to adapt to the environment where the force is deployed. They have to be secure, not giving any clue to the enemy of the maneuver of the force, or giving any piece of intelligence on our dispositif. And they have to be resilient. That is to continue to operate, either if there is a breakdown or, for example, jamming or an aggression from the enemy. So it's really the telecommunications are the backbone of the command of the forces that are deployed. Secondly, they are used to synchronize the units, the tactical units that are present on the theater, and that's why they have to be agile, allowing the movement of the forces, and so adapting to the movement to the forces, and also allowing to give some unplanned services to be able to adapt to what is on the ground, what the forces are facing where they are deployed, and even if it has not been planned before. In the future, the foreseen usages in the midterm are really focused on the development of the cloud technologies, also on the on the theater in the tactical units, different tactical units. So there we think that these technologies will need larger throughput and even to the lower level of the tactical units. So that is one of our major concern. And the second, the connectivity has to develop and to, so as said, that the telecommunications have to be agile and they will need to be more agile in the future to allow to the collaborative warfare during amongst the forces that are even army forces, but also with the other services, so the Air Force and the Navy.
Okay, thank you, sir. So you talk about cloud, you talk about resiliency, but what are the main threats you are facing today on the communication domain during operation? Could you give us maybe some real or concrete examples?
Yes, so the historical threat is jamming, because if you want to communicate, you have to be able to reach the other person you want to communicate with. So being jammed is so jammers are the main threat when mostly where in a symmetrical battle conflict, right? So when it has been seen during the actual Russia-Ukraine conflict, where jammers have been used and to disturb the organization of the command of the forces. So it's a real threat, and in the French armed forces, we are really focusing on the return of the symmetrical conflicts, and it is a real concern. The second one is cyber attacks, because we have more and more intelligent telecommunication means. So we embarked technology from the IT. We want them to be agile, even intelligent. So the cyber threat is high and is developing. Even small groups have the opportunity to have cyber tools, toolkit, and being able to disturb or even take control of some remotely operated robots or drones. So it's the second one.
Okay. Thank you, sir. This is quite interesting. So about jamming, maybe first answer to that could be the use of line-of-sight laser communication solutions. Gimel, please, what do you think about them, and are they mature today, this loss laser communication?
Sure. So regarding line-of-sight communication, the technology is pretty mature. It's widely used in the commercial world. Today you can get off-the-shelf terminals that are capable of transmitting lights at 10 gigabit per second within a few kilometers. And of course, if you want to go longer ranges, the bandwidth will go down. So you could achieve a gigabit per second at, say, 4 to 5 kilometers. So line of sight is not critical. It exists, pushed by the commercial world. So it's already available for the military forces.
Okay, so following the words of Gimel, sir, do you think this laser communication for line-of-sight solution, so maybe more tactical way, could have some interest for your military operation?
Yes, of course. So first of all, we believe that laser will be harder to jam, of course, because of the directivity, and also. There are a substitution means to radio frequency telecommunication means, and for that we want. It is a solution to downgrade the radio frequency signature of the force, because of course when you have a command post with many mini emitters to communicate with different type of units and with different elongations, you have you may be a big spot on the map with all your radio frequency emissions. So it is more discrete, more stealth, and also laser could be a solution also to what we something that we would like to improve within on the ground, is that our command posts are currently mostly concentrated, so they are more. They could be targeted more easily, and to have command posts that are survivable, we want to disseminate them, to have them on a larger scale, and so laser communication could be a solution also to have these multi-position command post, not concentrated, and to have this threat of being bombed lower down.
Okay, so in order to dispatch the troops. Yeah. So if I try to sum up a little, we face spectrum threats today during operation. Jamming is one of them, for example, and the major one. One of the major points is, I would say, the big data stuff. So for the loss, the line of sight, it seems we have already some solution available in the market. But for the beyond line of sight, the problem to solve is basically how we can transfer terabytes of data from the middle of the desert or from a ship into an operating base. So I understand today that this is not really possible to realize this massive data transfer, except by, I would say, a logistic way, meaning physical hard drives by plane. So to cater these BLOS needs, I guess we will have to use space asset, including laser communication payload. So for a few years now, we see many space laser comms news in the press or in the media. The US Space Development Agency constellation is one of them, and this constellation will include ISL links or inter-satellite links in laser. So I propose to go now in space, and who better than Frédéric from the CNES can enlighten us about the laser communication space technology. So Frédéric, maybe could you explain us what is a space laser communication first?
Well, basically, it's what it is shown on the screen. An optical link is not so different from a radio frequency link. You still have two terminals pointing each other, transmitting and receiving an optical wave, which is a physical support of the useful information. This useful information comes with the modulation of the optical wave on its amplitude, on its power, on its frequency, on its phase, as it is the case for radio frequency technologies. The difference are the fact that the components are obviously specific to optical wavelengths. The reflector antennas you may have in radio frequency technologies are replaced by telescope, but you still need then to amplify the signal at the transmit side, to lower the noise as much as possible at the receive side, as it is the case in RF. Well, you still need also digital processing at both sides of the link to shape and to receive the useful bits. So basically, it's the same as classical radio frequency links, but technologies are specific to optical wavelengths. And maybe one major difference, which is illustrated here on your on the screen, is the fact that the link will cross a medium to which it will be more sensitive than at radio frequencies, because a radio frequency link, a SATCOM radio frequency link, may propagate through the atmosphere, through clouds, through turbulence, without having a major problem. I mean, power margin is generally enough to cope with these effects. For optical wavelengths, you have written here the adaptative optics brick in particular. This brick will be very specific to optical links because turbulence, we will see it later, I think, is a major problem of the propagation through the atmosphere at optical wavelengths, and it's an increased complexity with respect to radio frequencies.
Okay. Thank you, Frederic. Before talking about the limitations, what are the main benefits of this technology? I know it's high throughput, narrow beam, free spectrum regulation, I guess.
Yeah, I think you effectively mentioned the main advantages of optical wavelengths with respect to other way to transmit data. Optical frequencies offer very larger throughput when compared with radio frequency technologies. It comes from the available spectrum. When we compare the bandwidth which is available around 1.55 microns, which is the common wavelengths considered currently to design and develop further technologies, if we compare the bandwidth available at this band compared with the Ka band, for instance, which is one of the most common frequency for radio frequency communication, the available spectrum is around 1,000 times higher, larger than the RF spectrum. So with larger spectrum, obviously, you can have more throughput. It comes from the available spectrum, but also from the fact that the optical spectrum is not ITU regulated. You may know that around, let's say, a few hundreds of gigahertz, ITU share the spectrum, the available spectrum, between services. So it means that, for instance, Ka band for military communication are very close to Ka band used for civilian application, but each other cannot use the other part of the spectrum. At optical wavelengths, you don't have this kind of regulation. You don't need to coordinate with other users because beam, you mentioned it, are very narrow. So the risk to jam another user or to be jammed is very reduced, and so there is no need to regulate the spectrum. And obviously, for military applications, discretion comes with the narrow beam, which is an advantage for frequency coordination, but also for discretion. The divergence of the beam will be a few tenths of microradians, and so obviously it is very difficult to intercept and to jam it.
Thank you, Frederic. Maybe this is great benefits for honestly military operation. And about the main limitations, but I guess we have limitations.
Yes, there are limitations, and I already mentioned the fact that propagating through the atmosphere is one of the main problem we have and we will have when considering free space optics from space to ground. Obviously, there are some application cases where atmospheric propagation is not a problem. Optical intersatellite link, which are now being a mature technology, are not propagating through the atmosphere. So they have not to mitigate cloud blockage, to mitigate turbulence effects. We may also think that space to airplane communication, for instance, have less problem than space to ground or space to ship communication, because airplane may be cooperative. They can fly on top of clouds. They will not be in the most turbulent layer of the atmosphere. So these two applications are natively tolerant to atmospheric propagation. But for space to ground, indeed, one of the major problem is first the cloud blockage. And to mitigate this problem, you have, let's say, two ways to mitigate. One is to have site link diversity. If one link is blocked, you have to select another link which is not blocked at the same time. it is generally the system trick that is used when you want to have high availability. For CVN application, for instance, we look for 99.9% availability. So obviously, we need to have this link diversity. But you can also select application where this high availability is not a problem, is not a need, a requirement. So in that case, you may be tolerant to loss of availability, but when the link is available, you will have very high throughput to download or to upload the amount of data. Another limitation lies in the human safety, the eye safety. Indeed, it's like a laser you can use in conference. You need to be sure that the laser will not be risky for human around the laser, because the optical wavelengths are quite close to the visible spectrum, the eye visible spectrum, and so you have to respect the laser safety regulation and to check it before deploying an operational application, that you will not create a risk for someone on ground, someone in air, and even for space application, someone in space, like ISS, for instance. And a last limitation or last technical problem to solve comes directly from the advantage of optics. You mentioned the fact that the beam is narrow. So we saw that the narrow beam is an advantage for discretion. It's an advantage for frequency regulation or no regulation. But it creates something not existing in radio frequency communication. You need to point the two terminals with a very high accurate precision. And indeed, if you don't point in the microradian class, you will decrease the throughput because you will lose too much power, and so the throughput will decrease. So if your need is to have high throughput, you need to guarantee a very reliable pointing accuracy. And yes, the order of magnitude is generally a few microradians to a few tenths of microradians.
Thank you, Frederic. Maybe, sir, following that, you would like to add an operational view on top of this? Do you think these benefits can give you an operational superiority on the field, especially during a high-intensity combat?
So yes, even if the cloud blockade is really a drawback that cannot be, that signifies that laser cannot be the main command link because of the need to have permanent and real-time command links. Laser from satellites can be useful for example, the links with the airplanes was mentioned before. So using satellite links, laser satellite links to upload large amounts of data that we have available on our ISR drones and other ISR platforms could be a solution. And also I mentioned the growing needs of throughput that will be the consequences of deploying clouds even in the on the theater. And these clouds may embark large databases that could be synchronized whenever a high throughput link is available, so a laser link available, and that these databases don't need to be synchronized every time. It's not real-time data, so it is another application. And furthermore, I would stress another advantage of laser communications. It's when you are the beam is really narrow, and it's you cannot intercept a laser link, because if you do that, you are cutting the link. You are intercepting. So it's when in communication, another threat is to be able to be that the enemy is able to intercept what you are saying, what you are transmitting, and use it for its own purpose. And when doing that on a laser link, you will be informed that the link is down, so there is a problem, and you will stop to transmit critical or sensitive information. And it's also another application.
So I see we have some benefits, we have some limitations, but maybe I could say laser communication solution could find their place in military network. To sum up, basically in space between satellites, as Frederick mentioned it before, it is ISL, it is a mature technology. We will see it in a few seconds with a video of the Space Data Highway, which is a service already existing since many years, for many years. But between space and ground, the level of maturity is lower because of the cross-atmospheric challenges mainly, but we are arriving at a good level too. So we can expect concrete operational solution maybe in the next coming years. Am I right? Okay. So I propose to show you a quick video of the Space Data Highway, which is an operational services allowing the downloading of high-resolution imagery from low Earth orbit satellites in a near real time. And obviously, the architecture is based on a laser communication. Let's see if it works. Yeah. Normally there is some music too, but I guess no. Okay. Well, just the video. It's less sexy with the sound. Yeah, but maybe Maël, you would like to comment? It's AIRBUS.
Sure. So the EDRS, the European Data Relay System, those are two geo satellites operated by AIRBUS, thanks with the ESA support. So their mission is to basically download data from Earth observation satellites using a laser link. So we're connecting Sentinel satellites using a laser to a geosat and then repatriating the data to the ground with a K-band. So that so you see that. So LEO satellites using a laser link, only DRS, and then down to Earth. And so the benefits of that is that we can always connect those satellites to a geosatellite. So you don't need a very dense ground network for real-time application. You just have a geosatellite, and that's it. And you're always in visibility of that satellite. So in those kind of collapses where you need fast response, like a fire somewhere, customers need those data as fast as possible. So what they do is that basically connect that to the geosatellite. Data is coming in Germany within an AIRBUS anchor station, and then directly into the cloud. So those two lasers, those two satellites are operational. Those are 34 links per day. So it means that within an hour of discussion, well, at least one laser beam will be operational above your head. So the message that, well, thanks to ESA and the member states, laser is not a science fiction. It's working every day, and we're serving customers for that. Yeah.
Thank you, Maël. So the Space Data Highway is an operational service, but how do we succeed to build this solution in Europe? Could you talk about the history? I see we have a great timeline here.
Sure. All right. Yeah. So the story started in Europe. Europe has been pioneering on lasercom for the last 20 years. So the story started in France with the SILEX program. So we had an Artemis Geo satellite connecting to a LEO satellite, just like the EDRS. The LEO satellite was Spot 4, Spot 4, and that was a world first. We demonstrated that in Europe, in France, that we could connect a moving satellite to a geo satellite. That was a world first. And then we continued in 2006 on a Mystère jet plane. In the Bourget, we demonstrated that we can fly a laser terminal in the air and connect that to a geo satellite. So that was the world first in the Bourget. And following Frédéric's comments that when you're dealing with lasers the beam is so narrow that the complexity to maintain the link to a geosatellite, it's non-trivial. So by doing this demo, we show that you could maintain that. You could completely master this challenge of maintaining the beam. And we're not just talking about just for a few seconds. We're talking about maintaining it for a telecom mission. So that was the Lola experiment, 50 megabit per second in a near visible spectrum. And then the story continued in Germany. So from 50 megabit per second on Artemis, we went to 2 gigs, 1.8 gigs to be precise. And with AlphaSat as a precursor, we demonstrate that we can have an operational service. That's the European Data Relay System, the Space Data Highway. It's still operational, available. And since then, every year we'll orbit space assets in space. So with the Pixel mission, enriching ADRS with Pléiades Neo on LEO orbits, and then several direct-to-Earth missions. So on the UK program and on LASIN. So the goal is to demonstrate that we can directly dump data from the low Earth observation satellites directly to Earth on an optical station. So if you're super fast on the bandwidth, well, you don't need so many revisits. So with very low complexity terminals on the ground, you could basically dump those data directly without going to a GeoNode. So this is ongoing. And then the story continued back in France, thanks to the CNES, to the agency support. We're going to fly Teleo, the Teleo mission. That's going to be the largest, to me, the largest optical terminal on a geo orbit. That's going to be a massive one. And the goal is to, as Frédéric explained, we want to show that we can go through the atmosphere. So we've shown that in the past on Lola, but now we need to go on the ground and do that as a daily basis. One of the messages I'd like to bring from the industry is that many demos have been done. The goal is when an industry can commit on the performance. We're talking about injecting light, as you explained, injecting light into a hole which is thinner than a hair. And that hole is 1,000 kilometers away, 4,000 kilometers away. And you want to inject light in there. And the problem is that you want to do that, but you're in a noisy environment. The atmosphere will completely destroy your wavefront. So the thing is, how do you maintain that, but all the time? We're talking about 99% of not missing the target. And that's the key. So we're switching from a demo era with a lot of different partners doing a fantastic job around the planet. We're switching from that demo era to operational systems. As ADRS is paving the way to the system, we're going there because we see more and more businesses and institutions needing to connect not just space to the ground, but ground assets between each other using space. So this is where we're paving the way, thanks to the agencies for the future. So that was Teleo, Ultra Air, of course, to go back in the air at super high bandwidth using ADRS, and then the future, the next generation. So there is a co-op project, Frédéric may say a few words. The co-op project is not to go at few gigs, but going to terabit per second, pulled by the commercial need. So we're building that with a big ecosystem in France, with more than 15 companies. And the goal is to go through the atmosphere, super high availability at 1 terabit per second. So again, through the atmosphere.
Thank you, Guimel. So I see, I understand, the CNES was part of many of these missions, of these great projects. And I know, understand that Teleo is key, is strategic for characterize the atmospheric channel, and so at the end to build some industrial solution and some concrete product. Frédéric, on this point, for the operational use cases, do you think the space to ground technology is mature enough now, or will be mature enough to do that in the next coming years?
Yes, I think the time frame which is on screen here shows the ambition. We prepare with various framework and various type of activities our French industry to be ready to bid in 2024. It is also true at European level because the European Space Agency has also a very ambitious program with the Skylight program to develop technologies at European level and to have more complex, even more complex demonstration at the end of the decade. So the problem is what Guimael expressed. The problem is to switch from the demo phase to the industry committed phase. And for that, for sure, next demonstration will be key, as it was key when performing Silex and then AlphaSat and the first EDRS node to convince that optical intersatellite link may become an operational technology. Now, OISL is a mature technology. All constellation, either civilian or even military, I think you heard about SDA in the US, all these constellation, civilian or military, they should use optical intersatellite link because 10 or even 15 years ago, there was this first demonstration paving the way. For the space to ground, we are now in the phase where demonstrations are preparing. Teleo should happen hopefully in 2023. Other demonstration at worldwide level will happen also. ICALI in Japan, for instance. Probably also demonstration from ESA a few years later. This demonstration will be key not to show that you have the world record of the throughput during 2 minutes, but that you are mastering to guarantee a reliable link 24 hours per 24 hours and 7 days over 7 days. That's the key element to demonstrate before the industry can commit it and before the operational user, either civilian or military, may adopt these technologies. So the time for demonstration for space to ground is not finished, but we see the arrival line to some extent. And we have also in the time where we are developing these technologies, because space to ground technologies are not exactly the same as for optical intersatellite link. Optical intersatellite link, it's okay. It's an operational technology. But for space to ground, we have to design larger telescope, onboard telescope, to have more powerful high power amplifier. Because we are targeting 100 gigabit per second per wavelength, we need the digital processing modem able to process this, inherited from ground technologies, but we have to adapt them to spatialize them. So we are also in the time, in parallel of this demonstration, to design and develop this, all these technologic bricks that will be part of further operational systems. And we have several programs ongoing. At French level, we have the France Relance Co-op project. CNES is supervising it, but it aggregates 17 industry companies led by, the consortium is led by AIRBUS. And we have a lot of companies which are present here in Eurosatory because they are also players for other application of optical wavelengths. And this core project should prepare the ready to bid in 2024, as well as the Skylight ESA program will increase the European ecosystem of industry players, as well as in other continents, in the US, in Asia. You have also this technology development. So we are in the time where we can hope that 2025 will be the milestone where this space-to-ground link may become operational and adopted by operational users.
Thank you, Frédéric. Maybe just to be clear, we talk about Teleo. Teleo, it's the BRDR8 on the slide because it's the name of the hosted payload, which will be on the BRDR8 satellite. So I see we have a great ecosystem in Europe, basically, capable to construct the next solution, space lasercom solutions. Maybe you want to detail it a little bit, Frédéric?
Yes, the first ecosystem we can mention is one which is already mature. The one providing optical intersatellite links. So at European level, we have at least two main players, Minaric and Tesat, which are already proposing products worldwide, and they are adopted or they are demonstrating their capability in SDA. It was announced recently that they have compatibility check with SDA infrastructure.
Two German companies.
Yes, yes, two German companies, but it's not a pure German story because for space systems we have also Thales Alenia Space, which is developing its own optical intersatellite link terminals. It was announced that when Lightspeed, the Telesat constellation, will become a reality, it should be optical intersatellite link terminals coming from Thales Alenia Space in Switzerland. So there is already this ecosystem which is matured. For space to ground, as I said, this ecosystem is getting more and more matured through big programs. At French level, it's COOP. At European level, it's Skylight. And and we are preparing from the component level until the subsystem level and even the system level. To give you an example, in COOP, I said we have 17 partners. In these 17 partners, you have AIRBUS, Defense and Space, which is a prime of space systems. You have also Thales Alenia Space, which is the second European prime of space systems. But you have also subsystem primes such as Safran, which is preparing optical ground station to be operated in these systems. You have also amplifier providers such as Lumibird or Silas. You have multiplexer designers such as Bertin or XBlue. So I would say the ecosystem is getting matured at all levels at the same time, from the component until the system, and it's really in the objective to prepare the ready to bid in 2 to 3 years for the space to ground civilian or military applications.
Thank you, Frederic. So I understand we have a quite complete ecosystem ready to build the next laser communication solutions. So it seems we should have more and more lasers in the sky in the next coming years, and can't wait to see that. Even if technically we won't see that because it is not in the visible spectrum, but I see time is running, so maybe we can keep some minutes to give place to the room. Do you have any question about laser communication? Well,
Thank you for this very clear presentation. My question is more about space-to-space links. What is the impact of optical communication on constellations, both on the constellation architecture and on individual satellites? Does it allow for lighter satellites, for instance, lower costs? What do you think?
Well, I think we would have the same answer. But basically, it enables to reduce the size of the ground segment. Because if you don't have optical intersatellite link to connect two satellites in a constellation, you need to have at least one ground station below the satellite that will serve the service area. So, for instance, if you have a satellite on top of France, but you have no ground station able to feed this satellite, you cannot feed the service area. With optical intersatellite link, you could have a ground station in the US propagating through one satellite, through the intersatellite link, and serving a service area in France, for instance. So it's basically the first advantage is really to reduce the ground segment to be operated.
Maybe Mel, you want to complement? Yeah.
No, May, thanks. Just another comment. The beauty of the constellations is that it's pulling the space industry toward high volumes. So just one comment on that. When you see the work done by TSAT in Germany, they're doing a fantastic job to reduce the swap and the costs of those terminals. So it's a very specific market that helps the industry to co-invest toward super large volumes. And that's the key for constellations. And the cost of the ground, of course, I completely agree on that. Yeah.
I guess, yeah.
Thank you for the presentation. Mes respects, mon commandant. So you mentioned the limitation between space and ground. We understood that maybe from space to ISR, can you hear me? It could be a short-term solution. Could you elaborate on that? And is it something that's, could you develop on what use? Is it that live data sharing or more than that? And is it something that's already been in the pipes and running with the SDT patrouiller? Thank you.
So no, there is nothing in the pipe to answer your question quickly. But we are envisaging now to embark on our next generation MILSATCOM demonstration of laser satellites. So between geostationary GEO and LEO, and also between GEO to ground and being GEO to ground on the different type of platform we have. So ground, ship, and airplanes. For drones and ISR, it may develop in an incremental manner, but it's subject to demonstration first, and another time there is nothing in the pipe right now.
About the drone, we didn't mention it today, but in the US they did some experimentation, it's public, with a Reaper connecting with a laser communication to a European satellite.
Thank you very much. Thank you for the presentation. So I work on standardizations. I was interested to know if for interoperability purposes there is anything that's being done on standardizing the laser comms, and what is the state of the art in this domain?
It's a good question, because if everybody design its own waveform and its own protocol, it will be quite difficult to interconnect several types of terminals. It is at least addressed in two situations. SDA, for instance, for its constellation, is trying to check the intercompatibility of several commercial terminals. That's typically what they did with Minarik a few months ago. I think they will go on to check if two terminals which are not provided by the same customer may connect to each other. And in the space community, this standardization problem came quite early in the CCSDS. The CCSDS is a committee where all space agencies are talking about their own needs for telemeasure and telecommand at least, and where they share how they can be intercompatible. And for data download, direct to Earth data download at least, there are some CCSDS document stating what could be a low complexity protocol for a few gigabit per second data downlink, a high complexity one, and also for deep space, I think they introduced a description of what should be an intercompatible deep space protocol and waveform. So it's not the full story. It's not the end of the intercompatibility question and the standardization question, but it has been introduced in the design, in the development quite early, so we can hope that it will not be lost. And since also we will build technologies for the very high throughput, the 100 gigabit per second wavelengths, based on ground solutions, the modems that are already equipping ground interconnect network, we will share the same protocol. We will try to share the same protocol, the same waveform, physical layer, etc. So it's not the Far West to some extent.
Yeah, on this field, I think standardization is really a concern, because we are thinking about a concept of using that is already developed in the US, but using all space infrastructure to act as a relay for any kind of space assets, and so there is a standardization is key to allow, for example, European project on constellation to act as this type of relay of different assets from different countries.
And I guess in the NATO environment, we will probably see some STENEG in the next coming years.
Thank you for a nice talk. I have a question. In the situations where the laser link would be blocked, for example, by clouds, what is the idea to substitute those links? Are you thinking about hybrid RF laser, or so? What is the vision in that direction?
It depends on the application. It was one idea for civilian application to have effectively a basis of throughput that would be ensured by RF, and then to have the main capacity brought by optical links. But to be honest, now for civilian applications, we are more working on site diversity for high throughput satellite to be sure that each time we have the nominal link which is blocked, we will find another one which is not blocked. So at the end, it becomes also an economic problem to be sure that we have not to deploy hundreds of ground stations because it will not be efficient. And the other idea is to find a tolerant application tolerant to this problem.
Maybe sir? Yeah. Because I guess for military one, it's
exactly.
not the same use cases.
Yes, for the forces that are deployed, they are on a single point deployed. So we cannot count on the site diversity, and it's more on the cross technology diversity. So we have, as I said before, the telecommunication for the commanding the forces have to be permanent, and so they will remain in RF, even if the needs of throughput is growing. And the RF we have so fixed sized links, so proportionally the amount of data will shrink during the years, but we will have the opportunity of using non-permanent links to make bursts of data transmission, where for the applications that are compatible with, and it's the example of asynchronous database updates for mostly intelligence and so on.
So I see time is running, so I will try to sum up in a few words what we said today. I noted 3 major points from you guys. The first one is basically laser communication could cater some operational needs, especially for transferring massive amount of data or to maintain communication under threats. Jamming is one of them, for example. But they won't replace legacy radio frequency capacity. So it will be a complementary capacity, RF plus laser communication. Second one is part of the technology is already mature on the ground for the LOS or in the space for the ISL. And on the ground, the LOS solution could be deployed very quickly if needed. On the other hand, on the BLOS solution, beyond line of sight, we are arriving at a good maturity level. I think we can say that we switching from space demonstration to operational solutions, industrial solutions in the next coming years, concrete products. So a smile, guys, a revolution here. And I can't wait to see the astronaut from the ISS watching the last Top Gun movie in 4K resolution, thanks to LaserCom. So it will be great. So I would like to thank you very much, Gimel, Sir and Frédéric, for this round table, and I wish you all a great Eurosatory and enjoy Paris.